Welcome to the concept of power cycles under the head of process utilities. Now, in the previous lecture, we covered about the energy perspective of steam as well as energy perspective of hot oil. Now, while discussing this either steam or hot oil, there are certain factors which we need to consider, and those are attributed to the thermodynamics. Because while we are converting the water into steam, the thermodynamic laws, all the thermodynamic laws attributed to this one prevails. Similarly, if we are heating the hot oil from normal temperature to say 400 degrees Celsius or 350 degrees Celsius, then again various kind of thermodynamic law they come into the picture. So, while discussing with this temperature domain or temperature governed parameters in various heat transfer related systems, we cannot overlook the importance of various thermodynamics law, various thermodynamic cycles. And especially we all know that the various power generation and refrigeration aspects, they are always tutored by thermodynamic law. There are so many cycles as on date available through those tutored the power generation as well as the refrigeration concept. So, in this particular lecture, we are going to cover these thermodynamic cycles, those who are involved or theoretically they are attributed towards the power generation and refrigeration. Now, before we go into the detail of this thermodynamic cycles, we must know some introductory remarks, like the engines, they are the thermodynamic system, they used to generate the net power output. Usually as a consumer, we require the net power. It is highly, we never bother that how these power are generated, what are the different principles involved in the generation of the power. Now, this produced power can be used in variety of applications, which can be termed as a work done by the system. This is the usual thermodynamic law. On the other hand, some devices, they are used to extract heat from the colder environment and deliver it to the hotter environment. These are termed as the refrigerator. Best example is your domestic refrigeration system, and next example is your domestic air conditioning system. So, the natural tendency of heat is to flow from hotter medium to the colder medium. Therefore, this in this second case, some external work needs to be incorporated for the heat transfer to push out the excess heat to deliver outside. Now, however, these both systems, they work on the principle of thermodynamic cycles. All we know that the things are tutored by these thermodynamic law. So, depending upon the type of work, these cycles can be classified into two categories. One is the refrigeration cycle and second one is the power cycle. Now, in terms of working fluid, sometimes these cycles can be termed as the gas cycle or vapor cycle. Now, in gas cycle, the working fluid, as gas does not change its physical state throughout the heat transfer. So, this is again a very good added benefit, and one example is the helium. In vapor cycle, the working fluid remains in the liquid phase in one half of the cycle and the gaseous phase or in the vapor phase on the other half, like steam. So, we have to consider this phase change and some in situ, the volumetric change or latent heat, whatever, all these things into the consideration. So, in terms of system used, these thermodynamic cycles are termed as closed cycle and open cycle. Now, in a closed cycle, the working fluid return to its initial state and can be reused for the successive cycle. So, one example is that a closed cycle gas turbine. We will discuss the theoretical aspect in subsequent slides. Now, in open cycle, the refilling of fluid is necessary for each cycle, as the fluid may get consumed or wasted in during the entire process. like open cycle gas turbines. So, here you can see there is a comparison between the closed cycle and open cycle. Now, fluid in the closed cycle, fluid with the better thermodynamic properties like helium, they needs to be used, whereas in open cycle we can use the cheaper fluids like air. In a closed cycle, the fluid remain intact in a closed compressing and heating chamber, and therefore cannot get contaminated in due course of time. Whereas in the open cycle, the fluid can get contaminated during the heating through maybe combustion or some other processes. Now, in a closed cycle, you can use the same fluid or you can recirculate every time this entire fluid. In an open cycle, you need to change the fluid or replace the fluid every time. Similarly, in the closed cycle, the fluid does not affect the life cycle of the system, that is the wear of turbine blades, etc. So, bit lesser the cost towards the maintenance would be low or minimal. In open cycle, contaminated fluid can affect the service life of the system. So, the maintenance cost or a wear and tear cost may be on the higher side. Now, the closed cycle, they are preferable for stationary installation and marine uses, whereas open cycle systems, they are best suited for moving installation. Similarly, the closed cycle, the high maintenance and installation cost, it is inherent of the closed cycle, whereas open cycle, because of the variety of the choices, the maintenance and installation cost are bit lower. Now, let us take the example, because we are saying that we are tutored by these thermodynamic cycles. So, while considering the thermodynamic aspect, we must know that concept of ideal cycles. So, while considering the ideal cycle, there are certain assumptions need to be taken. This cycle runs smoothly and does not involve any kind of frictional loss, and sufficient time is to be provided throughout the cycle. The system runs in a quasi equilibrium during the expansion and compression cycle, and there should be no heat transfer and pressure loss to the surrounding, as the piping and joints are well insulated. So, these are the purely assumption with respect to the ideal cycle. Now, considering all these assumptions, we can establish an ideal cycle, which can help to understand the mechanism involved in the real cycle. Sometimes we are very much interested in the thermal efficiency of heat engine. So, this thermal efficiency of heat engine can be defined as the net work done by the system divided by the heat input to the system. And you see that Carnot cycle, it is a very popular cycle. This was proposed by the Leonard Carnot. Now, it gives a thermodynamic interpretation of maximum possible efficiency that could be obtained from a heat engine. So, it put forward one limiting effect, that gentlemen, you cannot go beyond this particular limit. So, whatever effort you are putting forward to surpass this particular limit will be futile. So, Carnot cycle is an ideal reversible closed thermodynamic cycle, which can be divided into 4 successive operations 1, 2, 3 and 4. First one is the isothermal heat addition from heat reservoir maintained at TH, leading to an isothermal expansion. So, this is the pressure and volume. Now, see, there is an isothermal expansion, we are keeping the temperature constant. Now, heat is absorbed by the system, that is the gas, and the net work done by the gas to surrounding. This can be calculated as, now from here, this is the original station, the system reaches to this station. So, W A V is equal to QH is equal to mu RT H ln V2 upon V1. Now, this is your V2 and this is your V1. Now the work can be calculated as from A, when system moves from A station to B station. So WAB is equal to QH is equal to mu RT H ln V2 upon V1. Now this V2 is the final volume, and this is the initial volume, final volume with respect to this particular isothermal expansion. Now second is the isentropic expansion from higher temperature to a lower temperature, leading to an adiabatic expansion. So this is your stage from station B to station C, and you can calculate the work done during this particular course of time. So from station work done from station B to station C, WBC is equal to mu R upon gamma minus 1 TH minus TC. Now I told you that usual thermodynamic law they are prevailing. So this is an isentropic expansion, so we are using this mathematical formula. Now the isothermal heat rejection to a low temperature at heat sinks, this leading to the isothermal compression. Now this is from station C to station D, right. Now the heat is lost to the surrounding during this particular step. So while calculating the work done on the system, again utilizing the same phenomena, that from work done from station C to station D, that is equal to QC minus mu RT C ln V3 upon V4. Now this is the final volume for this step, and this is the initial volume. Now the isentropic compression or adiabatic compression from low temperature to high temperature leading to the adiabatic compression. Now this system again considered thermally insulated, and the gas continue to compress to achieve the original high temperature. So your entire, with respect to that thing, the entire cycle repeats. So work done from station D to station A, from here to here, is equal to minus mu R upon gamma minus 1 into TH minus TC. So while calculating the net work on complete cycle, this we can determine with this mathematical formula. W, the net work, is equal to work done from station A to station B, then work done from station B to station C, and then work done plus work done from station C to station D, and plus work done from station D to station A. Now if we add all the work, will lead to this particular equation, that is mu RT H ln V2 upon V1 minus mu RTC ln V3 upon V4. So this is the Carnot cycle. Now we are interested in calculating the net efficiency of the Carnot engine. So you can calculate the net efficiency by W upon Q1, or W is equal to Q1 minus Q2 upon Q1, or 1 minus Tc upon Thy. Through this way you can calculate the net efficiency of the system with respect to this particular Carnot cycle. Now sometimes we are interested in establishing the relationship between temperature and entropy, or temperature or pressure or volume curve. So you can see that here the temperature and entropy, this is the adiabatic compression, this is the work output, then isothermal compression and adiabatic compression. During the adiabatic compression, then the entropy remains constant. Then this is the heat input and heat output. So you can establish the relationship. Similarly, we can have the Carnot vapor cycle, except for the working material, which is steam. The theory of Carnot vapor cycle is identical to that of thermodynamic cycle. So any type of steam can be used: moisture containing, dry steam, saturated steam, superheated steam, and this is your Carnot vapor cycle. Now here again, if we try to establish the temperature versus entropy, or pressure versus temperature, you can see that here this is the adiabatic compression, and during this course of time this is the isothermal expansion. So whatever work being carried out over here, and then it goes to the adiabatic expansion, and again it goes to the isothermal compression, and system is again regain its value. So, you can calculate the net work being carried out in this particular system. Now, at a fixed temperature TH in the previous diagram, fixed temperature and a pressure, the water is isothermally transformed into the dry saturated steam. Now, this point B expresses the dry steam. Now, temperature and pressure remain constant from A to B. Now, we know that the water's latent heat is the heat it absorbs during the conversion to the dry steam. So, heat absorbed, that is QH, you can calculate by S2 minus S1 into TH. Now, during the adiabatic expansion from B to C, no heat is transferred from the system. Therefore, entropy remains constant. Now, the dry steam converts into the wet steam by doing work to the surrounding, and temperature pressure reduces to Tc and Pc, this one. So, during the isothermal compression cycle from C to D, the wet steam's temperature and pressure remain unchanged and the work is done by the environment. So, the heat rejected to the surrounding, this can be calculated by Qc is equal to minus S2 minus S1 multiplied by Tc. Now, in the fourth and last step, the steam is compressed adiabatically till it reaches to its original temperature and pressure. Therefore, the net work to complete this cycle would be W is equal to S2 minus S1 into TH minus S2 minus S1 TC, or in other words W is equal to S2 minus S1 into TH minus TC. So, obviously, when we calculated this work, then we are interested in the Carnot efficiency. So, the Carnot efficiency for this entire cycle would be W upon QH, and W is equal to, we have already determined through this equation, S2 minus S1 into TH minus TC upon S2 minus S1 into TH. So, efficiency is equal to 1 minus TC upon TH. So, the Carnot efficiency for this particular cycle or Carnot vapor cycle is represented like this. Now, it should be highlighted that a steam engine operating on Carnot cycle is impossible. The obvious explanation for this is that the isothermal expansion from A to B will have to be done very slowly in order to keep the steam temperature maintained at TH. Now, as a result, the isothermal compression from C to D will have to be done very slowly. However, in order to achieve the optimal adiabatic condition, adiabatic expansion B to C and adiabatic compression from D to A should be performed as quickly as feasible. And we know that in practice the rapid change in engine speed are impossible, practically it is impossible. So, furthermore, it is extremely difficult to completely eliminate the friction between the engine's numerous moving parts, and there are heat losses owing to the conduction, radiation and other factors. So, therefore, we cannot achieve the complete or efficiency or 100% efficiency. Now, apart from this Carnot cycle, there is another cycle which is very popular, that is called the Rankine cycle. This can be considered as an ideal cycle for vapor power system. We discussed this vapor power system in the previous one. Now, by superheating the steam in the boiler and condensing it fully in the condenser, the impracticalities associated with the Carnot cycle may be removed. So, you can say that this cycle tries to overcome certain of deficiencies of Carnot cycle. Now, here this is the conceptual diagram, that is heat in the boiler, then it performs some work in the turbine, that is the work out, then steam will get condensed so that the remaining heat you can extract it, and again whatever condensate is you can pump it with the application of work to the boiler. This is a simplified diagram of this Rankine cycle. Now, it work in a nutshell, you can say that in work it work with by converting water into steam in a boiler, which expands through the turbine to producing the useful work. It converts into the heat into the mechanical energy, which can be further transferred to the electricity by using the associated utilities. Now, Rankine cycle can also be divided into 4 successive steps. That is the pumping. It used to increase the fluid pressure using the compression cycle. Now, work is done on the system at this step. Now, as the fluid is water, which does not change its volume during the compression, incompressible, which is an isentropic process. So, you can draw the PV diagram accordingly. Now, second is the boiler. The compressed fluid is heated to obtain its higher temperature, that is its boiling point, converting it into the high pressure steam. So, heat is supplied to the system and the pressure remains constant. It is an isobaric process, this one. Now, third one is the turbine. The high pressure steam get expended while doing work to convert the pressure energy into the mechanical work. So, work is done by the system and pressure is reduced. So, this is an isentropic process. You can visualize this in this figure. Now, condensing. The unutilized heat get transferred to the heat sinks in this step, and the sink can be environment of water for preheating or some other process. It is an isobaric process. So, the release of heat is necessary to reduce the volume of fluid, otherwise it can directly reduce the efficiency of this pump. So, this is again a quite essential aspect of the process. Now, the steady state flow equation for unit mass of fluid, this can be written as Q in minus Q out plus W of work in minus W out is equal to HE minus HI. Now, this Q is the heat, W stands for obviously the work, H is the enthalpy of the system, and we have used this E and I, this stands for inlet, outlet, effluent or influent respectively. Now, for pump, this Q is equal to 0. So, work in pump is equal to H2 minus H1 is equal to V P2 minus P1, usual work equation, where H1 is equal to HF fluid at specified pressure, that is P1, and V is almost equal to V1, and it is the Vf, that is a fluid at P1, that is for the water. Now, for boiler, obviously W is equal to 0. So, Q in is equal to H3 minus H2, and for turbine Q is equal to 0. So, W turbine is equal to H3 minus H4, and for condenser W is equal to 0, work 0. So, Q outlet is equal to H4 minus H1. So, the thermal efficiency of Rankine cycle, obviously whenever we discuss the cycle, so we are always interested in the efficiency. So, the thermal efficiency of Rankine cycle would be net W upon Q in is equal to 1 minus Q out upon Q in. This is the thermal efficiency. Now, let us have a look about the prediction of actual vapor cycle. Now, the actual vapor cycle differs from the ideal Rankine cycle because you need to incorporate certain irreversibilities associated with the system. So, as a result of irreversibility in the various components, we have to look into the concept of actual vapor cycle. Now, fluid friction, sometimes this causes the pressure drop in the boiler, the condenser and the piping network between the various parts. Now, this requires a large pump and a large work input to the pump. So, sometimes you may experience the heat losses attributed to the poor insulation. This is again one of the cause to deviate from the ideal cycle. So, there are various things attributed towards the deviation from the ideal cycle. So, that is why we are always looking for the actual vapor cycle. Now, here you see that we are having one ideal cycle, this one, and of course, keeping in view of all irreversibilities and other things, we are having the actual cycle. So, always as an engineering perspective, we are looking for this kind of a deviation from the ideal behavior. So, this may be attributed to the irreversibilities in the turbine. The other performance or other reason for the reduced performance, they are attributed to the irreversibilities happening throughout the cycle, not to the individual component. Some to overcome such kind of a things, pump requires a higher work input for the compression. Turbine on the other hand, they produces the lesser work output due to the inherent irreversibilities, that is like making it non-isentropic. So, we have to look into these variables, these verticals while considering the actual vapor cycle into consideration. Now, question arises about the improvisation of efficiency of actual vapor cycle. Now, Rankine cycle efficiency can be increased by increasing average temperature at which the heat is transferred to the working fluid in the boiler, or decreasing the average temperature at which heat is rejected from working fluid in the condenser. So, that is the average fluid temperature should be as high as possible during heat addition and as low as possible during the heat rejection. Now, there are three ways to carry out this one. One is that lowering the condenser pressure, it lowers the average temperature. Superheating the steam to a high temperature, that increases the T high, or increasing the boiler pressure, that means T high, you need to have this temperature on the higher side. Now, this is related to the your actual vapor cycle prediction. Now, by this way, we are coming to the end of this particular lecture, and again if you are looking for more knowledge, there is one reference which is attached to this particular slide. Thank you very much.